Okay, talking about my free range turkey coming, pick it up in a few days. It's almost Thanksgiving. Okay, you take a turkey out of the oven. I'm going to call that T relative. Not because you usually do Thanksgiving with relatives, but relative to room temperature, okay? So okay, so at various times as follows. T in minutes. T relative in degrees Fahrenheit. Usually by 100 minutes, it's retarded up and doubled up. Okay. So it's how many degrees Fahrenheit above? Well, usually in the bags I use, it ends up being a little bit overcooked, but nobody minds that. So let's say it's 100 degrees above room temperature. So room temperature is 70 degrees, 170. Generally want to cook it at about 160. So usually it's hot, higher than that, usually close to 200 degrees. Okay, there it is. Okay, after 20 minutes, let's say it's down to 80. Okay. And then it's down to 50. And then it's down to 35. Okay. Now, what I want to do is, I want you to do this. You've got a calculator. And instead of log, log, let's use the natural log. If you don't have the ability to figure out the natural log, then go ahead and use the LNG log because it's a simple conversion. Okay. But I think if you have one, you have the other. So I think everybody can do the natural log. Okay, well, your table then looks like this. I'm not sure about the 4.3 and the 3.9. I'm not sure I've rounded all these correctly, but that's what we're going to see. And I see that the top of the screen isn't visible. So there it is. I'll go up and then zoom in a little bit. Okay. Okay, so again, with the temperature above room temperature as a function of minutes. The relative temperatures are 180, 15, 35, minutes 0, 20, 60, 100. And oh, yeah, I kind of estimated these wrong. Because these are evenly spaced. This will probably be more like 4.4. And this will probably be close to 4.0. However, you've got the accurate numbers. Okay. Now, if I graph this information, I've got 100 here. So 60 will be about here. 20 will be about here. And maybe more like here. That's all I have the first time, but it's okay. Okay, so now I've got 4.6 here. I'm going to do a relatively honest scale, 3.6. Will be here. So at 100 we have 3.6. At 20 we have 4.4. So let's see, 4.6, there would be 4. About 2/3 of the way up here. And at 60 we would have 4.0, which would be about here. Okay. Now look at your own graph. The graph is going to be pretty much a straight line. Little fluctuation from the straight line, won't be perfect. You're going to have a graph that's pretty much a straight line. Okay. Now, another way to graph this to see maybe a little better if these points really do lie on a straight line. You can graph this in a window where you're going from 0 to 100 here. And I don't need all this space between 0 and 3.6. Really, what I want is 3.6 here. And 4.6 here. Now, if I do that, I have a point here. Let's see, 60 will be about here. And 20 will be about a third of that. I might have 20 about here. Let's see. Pretty close. Okay. Now, 4 would be halfway between 3.6 and 4.6. And 3.8 would be about here. And 4.4 would be about here. And now I can plot my points a little more accurately. And now doing this by hand, so nothing's going to be completely accurate. Here's a point. And then 64.0, that would be out about here. And 3.6, 100 would be down here in this point. Now we see that this point is a little low for a straight line. You don't see that as well up there because the line doesn't have as much slope. So the vertical differences between points are smaller and it's harder to see them. If we graph it in this window, and you should understand how this window represents. Same thing I've got here, but scaled a little better. We want approximately a rectangular, fairly close to a square window. And this isn't quite square, it's a little longer than it is high, but it still shows the behavior. So if I say, well, the graph is a straight line from here to here, I'm ignoring the fact that these 2 points lie below the straight line and aren't influencing my graph at all. I want these points to influence where I draw my straight line because I want my straight line to come as close as possible on the average to my points. I get much closer on the average, and really we're trying to do the square of the average distance, but leave that to the statistics class that actually talks about what's going on. So a better graph might come just a little high here and a little low here because it comes much closer to these 2 points and not that far from this one or this one. Okay? That might not be the best line. You could actually take a piece of string and manipulate it around and see just where the line ought to be to come as close as possible on the average to the points. Now, you do have regression analysis on your calculator. And I really don't even want to use that in this course. That's the statistics course. The calculator sort of things. I really prefer that you graph these things by hand. It tells you more about what's going on. Well, now, can we estimate the equation of this straight line? What's the y-intercept? What's the slope? Okay, so what we have here is, in this case, it's natural log. That's better. Here we're graphing natural log of t. T relative. And here is t. So it's like we have y equals mx plus b, but instead of x, we've got t. And instead of y, we've got the natural log of t relative. On this axis. So instead of y equals mx plus b, we've got the natural log of t relative equals slope times T plus B. Okay. In other words, we don't have Y here, we have natural log of T relative. We don't have T here, we don't have X here, we have T, but we're just replacing Y by what the vertical coordinate really is, and X by what the horizontal coordinate really is. You still estimate M and B the same way. So what I'd like you to do is estimate M equals and B equals. Just looking at a reasonable graph of the natural log of the relative temperature versus time. What do you get? I don't know. Okay. Okay, so that we've graphed this, and then we graphed it in a window that shows better how the points vary from a straight line. This is too shallow. The changes in the differences in the distances of the points up above and below the line aren't real clear. If you do this, they're clear. Now, of course, this was hand graphed, so there's some errors involved with that. But we then sketched this blue line that we think comes about as close as possible on the average to the points, the data points, the 4 data points that we have here, based on the data that we have here. Okay, well, we graph it in a closer to a square window so that we can see those differences. We just have 3.6 to 4.6. That's all we really need. We just need this in the whole here. And over here, of course, we need p-values from 0 to 100. Graph the points, and we sketch a straight line that we think comes as close as possible on the average, an honest attempt to make the line close to the point. And then we notice that this is a y equals mx plus b. It's a straight line. But y is natural log of t relative, and x is t. So now it's natural log of t relative versus t. Slope and y-intercept are just as you see them on the graph. So some people are using 4.6 for this point on the graph for the y-intercept, but it's clearly a little bit below that. And we're clearly a little above 3.6 for the y coordinate here. So we don't want to use this and this. That would just be the straight line from here to here, ignoring the effect of these points. Why do we have this data if we're just going to use this and this? Okay. What we have is we have 4 points, and our confidence in our model is going to be determined by how well the 4 points are approximated by a straight line. It might be that they aren't approximated well at all by a straight line, in which case this won't be a good model. Well, anyhow, so we've got to estimate M and B as we see it here, and then we've got to fill in M and B, and then we have an equation for T relative is a function of T. And we'll be able to change the form to exponential form, and we'll get a really good model. Okay. Now, one of the first things I emphasized early in the course is fundamental triangles, and I'm still not seeing them in any uniform manner. Once in a while I see one, it's usually not labeled correctly. When I want to review what labeling means, I've talked about it many times. So if I take 2 points, it's best to use 2 points that are separated by some distance. Okay. So I could use this point and this point as a basis for my fundamental triangle. And I draw the fundamental triangle. Here we've got it. And I label these points. Now I don't have a lot of room to label the points here, so I'm going to redraw the point is 4.43. No, 4.5. That's my estimate of where that point is, because here's 4.4 and here's 4.6. It's a little closer to 4.4 than 4.6. Let's say, sorry, 4.5 and 4.6. A little closer to 4.5 and 4.6. So I'd go 4.52 or 4.54. Using a good, large, not picking on everybody, but there's one person who could. Okay. Really nice graphs, but they're really small. The bigger your graph is, the better you're going to be able to estimate things. Okay, anyhow, 4.53 down here. Okay, we'll use 100. And here's 3.6, here's 3.8, here's 3.5. I'll say 3.65. So now I run. And I really want to see all this good. I don't keep writing it for my own benefit. I keep writing it hoping you'll imitate it. Okay? Run equals. And yeah, everybody in here is doing pretty much okay on this exercise, but you want to nail down these little details. Okay. The run is from 0 to 100. So it's 100 minus 0 equals 100. And the rise is 3.65 minus 4.5. Okay. That equals 1.12 or negative 1.12. So the slope is rise divided by run, which is negative 1.12 over 100, which equals negative 0.0112. Put that in a box right next to the hypotenuse. That's a completely labeled fundamental triangle. And this is what I want to see when I ask for a completely labeled fundamental triangle. Okay, not skipping any steps. I mean, if you've got the right answer, I know you go through the steps, but I want to see the steps because documentation is extraordinarily important. One of the things that we simply have to learn how to do. This is how you communicate what you did. You communicate is one of the aspects you're really trying to emphasize college life. Okay, what are those soft skills? Okay, so now we get the slope is negative 0.0112, and the y-intercept is 4.53. Well, now, all this, I have room to do it here, so I'm going to kind of go through here from up here and get to the final result. Can I see the top of this thing? Yep. Okay. So we get natural log of t relative equals mt plus v. M equals negative 0.0112. V equals 4.53. The natural log of t relative is negative 0.0112 t plus 4.53. So what's t relative? Can you solve this for t relative? Well, it should be automatic to you. The thing you're trying to solve for is bound up in a log function, so you change to exponential form. Now, it's a natural log. The inverse of the natural log is the e to the x function, right? But you know, it's basically exponential function. So t relative is e to the negative 0.0112t plus 4.53. Well, this is e to the 4.53 times e to the negative 0.0112t. By the rules of exponents. Okay, base to this power plus this power is the base to this power times the base to this power. That's the rule of exponents. A to the b plus c is a to the b times a to the c. And it's essential to have your laws of exponents straight right now, or at least by the time we get to the final exam. Okay. So e to the 4.53 is probably somewhere around 35. Say 96. E to the negative 0.0112. This is an exponential function. We can determine how long it takes the Turkey's temperature to relative temperature to drop to half. Okay, half of whatever it started at, or any time. Okay. Now I'll point out that the graph here looks like this. Okay, we've got 100, and then we got 35. Here's 100. And the graph is an exponential graph. This exponential graph, when we do the natural log of t relative versus t, transforms to a straight line graph. We can very accurately estimate the slope of a straight line graph and use the equation of the slope and intercept. Okay, the equation of a straight line, whatever the equation is, that's going to give us a natural log equals some linear equation just like this. We change it to exponential form and we get our exponential function. Now, what you get in the open math talks about semi-log graphs. This is really a semi-log graph. Okay. You probably don't have semi-log paper, although it's going to ask you to do everything on the computer, which is kind of ridiculous. But that's the best you can do with this kind of assignment. I recommend that you follow this procedure and see that you get the same thing, because this is very important to interpreting data. And I probably ask you to do this sort of thing on the exam. Now, what we have left in the course is fairly straightforward stuff. It's not very deep in most cases. You just learn to do it. It's just solving simultaneous equations and doing partial fractions. Okay. Not that you should relax at this point, but the conceptually difficult stuff is pretty much over. Okay. It's going to do some operations that are very important. And there's a lot of conceptual depth behind the operation, especially the simultaneous equations, because that underlies linear algebra, which is extraordinarily important in understanding the universe, understanding quantum mechanics, understanding all kinds of stuff that you're probably never going to pursue. Okay? So there's a lot of depth implicit in these calculations, but you're just getting what you're likely to need in future courses. Okay? So we don't go in to all the depth. You know, I'll restrain myself talking about the depths of quantum mechanics, which I understand very well myself. Most people don't. And most physicists who work in quantum mechanics don't, but they understand it a lot better than I do. Okay, so there we have it.